You're here because you want to get straight to what matters, really understand these breakthroughs without, you know, getting bogged down in technical jargon. You want that aha moment. Welcome to the deep dive.
Hello.
Today, we are diving into a really significant leap, I think, in quantum computing. Google's newest quantum chip, Willow, it seems state of the art.
Yeah, definitely. And we've got some great material to work with. We're drawing from a blog post by Hartmut Neven, the Google AI founder,
Right.
and also a couple of YouTube videos from the Google Quantum AI channel. They feature people like Julian Kelly, Hartmut Neven himself, Sergio Boiso, and John Preskill, the theoretical physicist.
Okay, excellent sources. So our mission today for this deep dive is basically to understand why Willow is such a big deal. What's the potential impact here?
Let's jump in.
Okay, so one of the things you always hear about with quantum computing, it's the errors, right? These qubits, they're just so fragile.
Exactly. That's the core problem. They lose their quantum state, their coherence, really easily to the environment.
Yeah.
It's been the major hurdle for a long time.
And Willow apparently does something different here.
Well, that's what's really exciting. The breakthrough with Willow is how it tackles errors. As they actually add more qubits, the error rate goes down exponentially,
Yeah.
which is, kind of counterintuitive for complex systems.
Yeah.
Usually more parts means more problems.
More things to break, yeah. But here, scaling up makes it more reliable.
Yeah, it's the key finding.
Okay, the sources talk about this idea of below threshold error correction. That sounds important. What does that actually mean?
It's been the goal since, gosh, the mid-90s, really, since the theory was first laid out. Below threshold basically means you've reached a point where your error correction scheme actually works better and better the bigger you make it.
Okay.
So just by adding more physical qubits working together as one logical qubit, you can suppress the errors more and more effectively.
And Willow achieved this.
Yes. They demonstrated it really clearly. They scaled up their encoded qubits, like in a grid pattern, from 3 by 3, then 5 by 5, then 7 by 7.
Right.
And each time they scaled up, the error rate was essentially cut in half. That's the exponential improvement we talked about.
Wow, having the error rate just by making the grid bigger, that's huge.
It really is. It shows the error correction is fundamentally working as intended, which hasn't really been convincingly shown before like this. It's like finally proving the blueprint works in practice.
And they mentioned something called beyond break even. What's that about?
Ah, right. Beyond break even. That means the encoding qubit, the logical qubit made of many physical ones, actually lasts longer. It stays coherent longer than the individual physical qubits it's made from.
So the correction isn't just fixing errors, it's actually extending the useful lifetime of the information.
Precisely. It proves the whole system is more stable than its parts, which is why Neven calls Willow the most convincing prototype for a scalable logical qubit built to date.
That is a strong claim.
Okay,
So
yeah.
it's not just bigger, it's smarter, more resilient. A fundamental step towards fault-tolerant quantum computers.
Exactly. Which brings us to the other major achievement. The raw computational power.
Yes, the random circuit sampling benchmark, RCS. This is where the numbers get kind of wild, right?
They do. So RCS is basically a task designed to be, well, relatively straightforward for a quantum computer, but incredibly difficult, practically impossible for even the best classical supercomputers as you scale it up.
Why is it so hard for classical computers?
It involves calculating the probabilities of outcomes from a really complex random quantum process. The number of possibilities just explodes exponentially, way beyond what classical machines can track. It's become a standard way to show beyond classical ability.
In Willow's performance.
Well, Willow completed the specific RCS benchmark they ran in under 5 minutes.
Okay, 5 minutes. And the comparison.
The estimate for Frontier, one of the world's fastest supercomputers today, to do the same calculation, is around 10 septillion years.
10 septillion. That's 10 to the power of 25, right?
Yeah. As Devin points out, that's vastly, vastly longer than the current age of the universe.
It's hard to even comprehend. So for this kind of problem, classical computers have just hit a wall, essentially.
A very hard wall. And it shows the potential, as John Preskill mentioned, for this double exponential speed-up quantum computers offer for certain problems.
The blog post even mentioned David Deutsch's multiverse idea, suggesting the computation happens across parallel universes.
It does touch on that, yeah. It's a fascinating theoretical angle.
Huh.
But practically speaking, as Sergio Boico highlighted, the result just starkly shows this widening gap in capability for certain tasks.
And they acknowledge that classical methods have improved since Google's first quantum supremacy claim in 2019.
Oh, absolutely. Classical algorithms got much better, faster. There's this constant back and
A
forth.
computational arms race, almost.
Sort of, yeah. But the key takeaway is that while classical methods improve, the quantum processors seem to be improving even faster, at least for these specific benchmark tasks.
Yeah.
The gap is widening.
Okay, so incredible error correction, check. Off the charts, computational power on RCS, check. Let's look under the hood. What makes Willow tick? The hardware details.
Well, it has 105 qubits, which is, a decent number. But the team really stresses that their focus is on quality over just quantity.
Better qubits, not just more qubits.
Exactly. And that quality is what enables the performance and error correction and the RCS benchmarks.
I saw something about T1 times improving significantly. What are T1 times again?
T1 time basically is how long a qubit can hold onto its energy,
Yeah.
stay in that excited one state before decaying back to zero. It's a key measure of coherence.
Longer is better, obviously.
Much better. Longer T1 means more time to do computations before the quantum state disappears. Willow's T1 times are now approaching 100 microseconds.
And that's a big jump.
It's about a 5-fold increase compared to their previous generation, Sycamore, was around 20 microseconds. And Julian Kelly made the point that they achieved this without compromising other important aspects of the chip.
5 times better coherence? That's serious progress. They mentioned their new fabrication facility, too, in Santa Barbara. How important is that?
Oh, immensely important. Having their own dedicated fab gives them end-to-end control. They can optimize everything: the chip design, the materials, the manufacturing steps, the gate designs, the calibration.
It's a holistic approach, as Nevin called it.
Exactly. You need that tight integration and control at this level to push the performance boundaries.
They also talked about connectivity and reconfigurability. Why do those matter?
High connectivity means qubits can easily talk to many neighbors, which is crucial for running complex algorithms efficiently. And their qubits and the connections, the couplers, are tunable.
Tunable how?
They can adjust their properties, which allows for very fast operations, fast gates, with low error. But the reconfigurability is really clever.
Yeah, what's that?
Julian Kelly explained it. If they find a qubit that's performing poorly, an outlier with high errors, they can actually reconfigure the connections around it, effectively isolating it or routing around it.
Ah, so they can dynamically work around faulty components?
Precisely. It helps make the overall device performance much more uniform and reliable, even if individual qubits aren't perfect. Plus, they have continuous software calibration running to constantly tune things up and minimize errors.
So it's hardware plus smart adaptive software working together. A very sophisticated system.
Definitely. Which leads to the big question, right? They've shown these amazing capabilities. So what's next? Where do they go from here?
Yeah, that is the million-dollar or maybe billion-dollar question. They've beaten supercomputers at RCS. They've cracked the error correction threshold. What's the next mountain to climb?
Hartman Nevin was very clear on this. The next major goal is demonstrating a useful beyond classical computation.
Useful, that's the key word.
Exactly. Something that solves a real-world problem and is genuinely out of reach for classical computers.
They made a point that RCS, while impressive as a benchmark, doesn't really have known practical applications yet.
Right. And other potential applications, like scientific simulations, are often still solvable, maybe slowly, but solvable, by classical machines. The goal now is to find something that hits both criteria, useful and truly beyond classical reach.
And what kind of useful things are they thinking about?
Well, the potential applications they mention are things like designing new pharmaceuticals, creating better materials for batteries, maybe helping with fusion energy research, discovering new catalysts for energy, big, impactful problems.
And the connection to AI, Nevin obviously runs the quantum AI lab.
Yes, he sees quantum computing as potentially transformative for AI,
Yeah.
helping process complex data sets, designing better machine learning models, simulating quantum systems for scientific AI. It's all intertwined in his view.
They laid out a roadmap too, didn't they, towards something commercially valuable?
They did. The long-term goal is a fault-tolerant computer with about 1,000 stable, error-corrected logical qubits,
1,000 logical qubits.
which they estimate will require something like 1 million physical qubits, maybe more, given the overhead for error correction.
Wow, 1 million. And where are they on that roadmap?
They have 6 milestones outlined, and they indicated they're approaching the 3rd one now. So progress is being made step by step.
And Nevin seemed quite optimistic about the timeline for actual applications.
He did suggest we might see early valuable commercial applications perhaps within the next half-decade, maybe just a few years, which is, quite soon in the grand scheme of things.
Very promising. Okay, so let's quickly recap. Willow seems like a major milestone. It's tackled quantum error correction exponentially, getting below that crucial threshold.
Check. And it's demonstrated computational power on that RCS benchmark that just leaves classical supercomputers in the dust by an almost absurd margin.
Check. And underlying this are real hardware improvements, better qubit coherence, the dedicated fab, this clever reconfigurability, tangible engineering progress.
Absolutely. It feels like they're building the foundations needed for truly useful quantum computers.
It definitely seems like this technology could revolutionize, well, almost everything eventually. So maybe a final thought to leave our listeners with. Considering this pace, this exponential progress, what problems that seem completely impossible today might quantum computers solve in, say, the next couple of decades?
Mm,
And how could that change our fundamental understanding of the universe or just what we're capable of?
that's a fantastic question to ponder. And for anyone whose curiosity is sparked, Google does point people towards their open source software like Circ, and they have educational materials, even of course, there are a course on error correction now.
Great. So resources are out there if you want to dive even deeper.
Definitely worth exploring. This field is moving incredibly fast.